All right, in this video, we're going to talk about slope fields and how they can be useful in terms of being able to determine what an original function is when you're given a differential equation. So remember what a differential equation represents. It represents the derivative of some function. And if I put in points into my derivative, I get the instantaneous rate of change of a function itself. Well, a slope field is nothing more than a bunch of small line segments that indicate basically anywhere for any point in a coordinate grid what the slope would be of a function. Now, it's actually very interesting when you look at the slope field because by looking at the individual slopes for each point, you can get a general shape or idea of what a general or particular solution may look like. And so what we're going to do here is we're going to plot a differential equation and make a slope field based on the fact that dy over dx is equal to 2 times y. So what you're going to do is you're going to plug in coordinates that lie inside of our viewing window to get slopes. Now, since we only have one variable in our differential equation, this one's actually going to be relatively simple here because everywhere that y is equal to 0, I'm going to have a slope of 0. So that means my entire x-axis is the slope, if it was to pass through any of those points, would have 0 slope. It'd be horizontal. And then I would work and say, all right, well, everywhere where y equals 1, dy over dx is going to equal double that, so my derivative would equal 2. So I would do the best that I could to make a slope that is equivalent to 2, and so I'm just going to say, okay, so everywhere that y is equal to 1, the slope would look something like this. So we'd say that that line segment would be equivalent to what a slope of 2 may look like. And then if y was equal to 2, the derivative, or my instantaneous rate of change, would be equal to 4, so it'd have to be steeper than that. And so everywhere that y would equal to 2, I'd make a line segment that would appear to have a slope of 4. So it'd be steeper than the one that I just did. And likewise, where y would equal negative 1, my derivative of y would be equal to double that, so it'd be equal to negative 2. And so I would have to envision what a slope of negative 2 may look like. And so let's just say that this here would be a slope of negative 2. And then if when y equal to negative 2, my differential equation says that the rate of change would be negative 4. And so it's going to be steeper in the negative direction. So we have a differential equation that will generate a slope field that looks like this. And so you're trying to figure out and be like, all right, well, what could that possibly represent? Well, let's say we know that we have the point 0, 1 is on the particular solution. So I'm going to use this coordinate and we're going to say, all right, so 0, negative 1 lies on this curve. And so I'm going to put a dot there. Now, when I work my way and I'm trying to sketch, what the slope field tells me is that at or around that given x value, we're going to match that slope. So I'm going to have that same slope right there. Now, by the time I get over here to 1, I have to have this slope here of negative 4. And so that doesn't mean that the curve is going to pass through this particular point, or in fact, actually the entire y values have that slope. So by the time I get to this y value, I'm going to have to be parallel to those slopes here. And so I'm just kind of work my way and say, okay, by the time I reach that y value, I have that kind of slope. And now I'm going to work my way back and say, well, by the time you get to this y value of 0, you have to be horizontal. And so I'm going to work my way up and say, all right, by the time I get to here, I got to be horizontal. And so we have an expression that we say, all right, well, maybe that's what the particular solution would look like. Now, the way we would actually find what the particular solution is to solve the differential equation by using the technique that we did in a previous video, which is separation of variables. So if I separated my variables, I would have dy divided by y is equal to 2 dx. We would integrate both sides. That'd give us the natural log of the absolute value of y is equal to 2x plus c. And we would write that as y equals, we would go e to the 2x plus c power, which is equivalent to y is equal to c times e to the 2x. We use our initial condition. We put in -1 for y, 0 for x. We solve for c, and we get -1 to equal c. And so our particular solution should have been y is equal to -1 times e to the 2x power. And we're looking and say, all right, well, this does resemble an exponential function where I have a horizontal asymptote. The fact that it's negative means that as you go to the right, it has to be decreasing. And so that's how we confirm our answer off of the slope field by separating variables. Now I want to do another one of these. So what I want to do is we're given a differential equation. We're going to use Desmos slope field generator, and we're going to look at a slope field that's already pre-made for us, and then we're going to graph two particular solutions on it. So here's our differential equation. Now I open up the slope field generator, and we type it in very carefully, and we get over here on the right-hand side of the screen what the set of possible what the slopes would be for a function that would generate this slope field through its differential equation. And it's kind of hard to come up with and look at this and say, wow, okay, what would the equation be that would create that? So we're going to try to solve the differential equation by doing separation of variables, and we're going to plot our particular solutions on the same graph to look at. Okay, so we have this differential equation. We want to solve it by separating variables. So I'm going to move my y's to the left, divide by the 3 minus y, multiply the dx to the other side, and then we're going to go through the process and we're going to integrate. And so I find the antiderivative of the left-hand side, and which would be -1 times the natural log of the absolute value of 3 minus y. And then I got equals, that would be sine of x plus c. Okay, and we want to try to get this to be y equals. So I'm going to divide by that negative there. And I divide by that negative, make negative sine of x. No, c is still that number to be named later, so I'm going to keep that as a plus c here. And now we're going to go through, we're going to take off the natural log function. So I'm going to rewrite as an exponential function. So we have 3 minus y is equal to e to the negative sine of x power plus c. And then we're going to write this, we're going to deal with the plus c, and we'll say that's 3 minus y is equal to c times e to the negative sine of x power. And I'm going to rearrange this so that way it's y equals. And so our general solution here would be y is equal to, we would have, I could write this as 3 minus c times e to the negative sine of x power. Now something else I can do, because c is this number to be named later, is that if you were to rearrange the terms, we could rewrite this as negative c times e to the negative sine of x and then plus 3. Now, so we'd have that. Now c being that number to be named later, I could just make this positive c instead of negative c. And so I could have c times e to the negative sine of x plus 3. And I could leave it like this right here and say, all right, there's our general solution that we're now going to find particular solutions for based on the points that are given. So our first point for a particular solution, we have the coordinate 0, 1. So I'm going to put in 0 for x, 1 for y. We're going to solve for c. So we get 1 is equal to c times e to the negative sine of 0 power plus 3. Well, sine of 0 is 1, or excuse me, sine of 0 is 0, e to the 0 is 1, so I got 1 is equal to c plus 3. So I subtract the 3, and I get -2 is equal to c. And so I put in -2 for c, and we get our particular solution to be y is equal to -2 times e to the negative sine of x power plus 3. All right, so then we go back in here into the slope field generator. We plot our point, 0, 1, and then we plot our particular solution. We look and see how it matches the little line segments that represent what the slope of the curve should be. And we see that the general behavior of our particular solution matches the slopes that are provided by the slope field generator, and it passes through that point, 0, 1. All right, so now we're going to do the same thing again. We're going to write a particular solution based on the initial condition that it has to go through the point 0, 4. So we're still going to use our general solution here. We just got to solve for c based on a new set of conditions. So when y is 4, x is going to be 0. So 4 is equal to c times e to the negative sine of 0 power plus 3. Sine of 0 is 0. E to the 0 is 1. So we got 4 is equal to c times 1 plus 3. And we get c to equal 1 here. So our particular solution that'll pass through that point, 0, 4, is going to be y is equal to 1 times e to the negative sine of x power plus 3. All right, and so we put that same graph on our slope field, and along with that point, the initial condition 0, 4, and we look here at Desmos, and we see how the general behavior of the curve in blue passes through the initial condition 0, 4 and matches the general behavior based on the differential equation. All right, last little part here. So let's say we're given slope fields, like what we have. So I got 6 of these. And I want to try to match the slope field with the given differential equations that I have over here on the right-hand side. So remember that a slope field, these little line segments, has to equal what the derivative equals at those given values. Now, there's some strategy involved with doing this. And what we do is we'll look and we'll try to pick out some functions that we can easily identify. And so something that I normally look for is I look at the graph and I try to find anywhere where the graph is horizontal. So let's look here at the top left. Notice how I have little horizontal line segments right here on this slope field. Now the y value of that slope field is when y is equal to 2. So when y is equal to 2, my derivative, dy over dx, has to equal 0. So I'm going to go look for a differential equation that will equal 0 when y is equal to 2. And so if I look at that, this differential equation right here will equal 0 anytime y is equal to 2. So that slope field belongs with the differential equation number 3. We look here at our second graph. Notice how everywhere that x is equal to 0, so when x is equal to 0 here, the differential equation dy over dx has to equal 0. So I want to go find out, all right, no matter what y is, when x is 0, my differential equation has to equal 0. So I go look at my list. And so I have options here. So that would be option number 4. And it also would be option number 2 in terms of when x is 0, the differential equation is going to equal 0. So I got to determine, all right, well, which one of these would it be? Now, there's some other key characteristics that happen. Is for this one, if y equals 0, we would be undefined. So everywhere that y was equal to 0, we'd be undefined. And so I go look and notice how everywhere here where y is equal to 0, I actually have a point where my differential equation is. I'm given a slope there. And so it would not be number 2. Now I could also confirm it's number 4 because everywhere that x is positive, I should have positive slope. So I got positive slope here, and then everywhere x is negative, I would have negative slope, so I have that. So that second graph would be number 4. Now let's look here at the third graph here. So this one's kind of interesting. Change colors. All right, so I'm trying to find some key characteristics for what's happening. And one of the first things that catches my mind is that I see this x right here in the middle. And so I'm looking kind of right here at this. So that part and this part right here to try to find some key characteristics for what's going on. Now, what those look like is those look like diagonal lines to me, where this first one looks like y is equal to x, and this second one looks like y is equal to negative x. And also, so in terms of what their slope would be, is that one here would be dy over dx is equal to negative 1, just because of slope-intercept form, and that one would be dy over dx is equal to positive 1. Now, I know we're only looking at 2 lines here, but that's an interesting part for me, because if we're on a coordinate plane, it's kind of hard to see where the points are in terms of x's and y's, but I have to, basically, along a diagonal, I have to have a slope of 1 or -1 and kind of see where that would constantly take place for a given set of x and y values. And what that means is that when x and y have the same values, no matter where you're at, so if x is 1, y is 1, I equal 1. If x is 2, y is 2, I equal 1. So we're looking at a ratio, and that would actually be this one right here. And so for this graph, dy over dx would equal x over y. This would be graph number 2 here. All right, now we're looking at a new one and trying to figure out, all right, well, what's going on here? Now we're looking, trying to get a general idea for what's going on. If I just come through here and try to follow a pattern for what's going on, we're kind of waving our way through here. And so I'm looking at and saying, all right, well, what are my options in terms of looking at a derivative that would create some kind of oscillating function? It has to be some kind of trig function, sine or cosine. And we're looking, and we have the differential equation, y is equal to sine, dy over dx equal to sine of x. And so the antiderivative of sine is cosine. So we have differential equation number 6 right there. All right, now we're looking here at another one to see what's going on. I want to figure out which one this is, and so I'm going to go find some key parts. We look, and we have these horizontal line segments right here. That means that everywhere that's happening is where my differential equation, dy over dx, is equal to 0. And so it's peculiar, but it does happen right there at the origin. And so I want to figure out, well, which one of my options left, option 1 or option 5, would have a derivative value of 0 when x is equal to 0. Well, e to the 0 power is 1. At 0, if I put in 0 for x, 0 for y here, I get 0. So this would be differential equation number 5, based on what we have left. Now, we can also test and put in x and y values and see if they would match the slope, but based on what's left, that's the only test I would need to do. And which brings us to our last one. Our last equation, differential equation here, would be e to the x. Now remember, the property of e to the x is that its antiderivative is itself. And so if I just drew a general sketch in there, and I would see that an exponential function would be the general solution there, that leaves me with number 1. So that would be the slope field for that differential equation.